Thanks for inviting me. And Tyler also, like, it was really great talk. And yeah, so let me go forward with this talk. So this talk is not essentially about only our recent paper. This is essentially about clubbing two similar works that I had. So I'm just gonna like go through that in this talk. So first, like a little bit of intro about myself. I'm a PhD candidate at McGill University and Mila, co-supervised by Joel Pinu and William L. Hamilton. And also I'm a research intern at FAIR Montreal. My research interests are kind of in intersection right now with systematic generalization, which is kind of a subpart of neural reasoning, and in discrete domains, such as in language or in graph. And also I dabble a little bit into dialogue systems. And originally I'm from Kolkata, India, and right now I'm at Montreal. So, okay, so why care about generalization? So ML models are getting really good at feature extraction. So those of you have like seen Joshua's stellar talk in last NeurIPS. He talked about this topic of system one versus system two deep learning. So what is system one? System one is where we are right now, where we have very good models which does feature extraction. So given a standard data set, that model like really performs quite well on that particular data set. And in the bottom right corner, you see that I have posted like a top one accuracy. This is taken from papers from code. And this is a top one accuracy on ImageNet. And right now the state of the art is just a little bit shy of 90%. So system one deep learning works really, really well. We have pretty good feature extractors, and also the number of parameters used by our models are like increasing like really, really fast. But what this talk is involving is I'm kind of trying to motivate towards system two deep learning. So this is reasoning which involves inductive reasoning. Basically when you learn some skills from your data set, you want to like apply those skills to some new data set, or those data sets which are kind of produced from that particular data set. And you want to transfer your known skills, and you also want to remember your known skills. So basically, this is a slide I've just like kind of screen grabbed from Joshua's talk, where he talks more about system one and system two deep learning. So essentially, the system two or the future is to go towards a set of models which are kind of more logically driven. So essentially, whenever you're making like a prediction, you are making that prediction in a logically valid way, so that you can reapply your learned skills on top of a data set which is kind of derived from the original data set. So that kind of helps us to go towards a realm of out of domain distribution. Out of domain is kind of ill-defined. Like you can just say that, okay, I train on a subset of images involving cats and I want to test on images involving dogs. But in case of the out of domain distribution, it's better to present it in this way, that if your model can learn the integral skills or the integral components that is driving a particular task, can your models use those components and reapply them to a new task? So that example that I gave, it will turn up to be, let's say you train on a subset of cats and whether you can recognize a new breed of cat. So how do you know your model is reasoning? So there are a lot of performance metrics that we look at, specifically accuracy, or in binary classification, AUC on held out test sets. But that is it. Like that is the only measure that we are interested in, mostly in deep learning research. So right now there's a lot of push of building more interpretable models. We also want to build a lot more integrated test sets. So essentially you just not say that, okay, on aggregate, my model is performing 90%, but what does it show? Like, does it show that where your models are failing and how they are failing? And even if they're failing, like their failures should be kind of systematic. And also, how do you guarantee that your model is just not basically rote learning features, like given a distribution which is somewhat similar, but not exactly the same, whether your models can learn on this kind of setups? And also, how do you evaluate the robustness of your model? So recently in natural language processing literature, a lot of work is coming up on adversarial attacks. And people have been shown over and over that with certain types of adversarial attacks, you can fool a lot of language classifiers and also a lot of image classifiers, and there's a lot of defense mechanisms are coming up. But again, like, how do you evaluate your model on that kind of robustness without having access to such kind of data? So the key properties in system 2 deep learning that I'm trying to propose is that we want to go towards systematic generalization. So essentially, we want to learn to extract the core skills of a task, and we want to learn to apply those skills to solve any task which can be produced from such rules. For example, if you are learning how to add, you're probably learning how to add, like, let's say, single or double digit numbers. But let's say on test time, if I give you like n digit number, then you should also be able to add, because it's the same skill. You're just applying it over a new distribution. So that is just a very trivial example, but in a lot of other cases, you want to be kind of able to extract the rules that are imbibed in your data set, and you want to make sure that your model like reapplies those rules. And you want to be invariant to noise. And to do that, your model must be logically valid. That is, if your model is like correct at certain examples, then it should be correct for those examples throughout a set of distributions. So let's say we take a simple example. Let's say an example can be a simple kinship relation game. Now, if I'm given you a text which says about a certain kinship relation between characters, you can, like, if I ask you, like, okay, how is Carol related to Justin in this case? Then you can easily say that, okay, Carol is the grandmother of Justin. Now, this kinship relations, we know, like, these rules that we already have learned from growing up. But the cool thing, what we do without realizing, is that we reapply these rules. So if I give you a long set of relations, and if I give you like a pen and paper, you can still solve that. You can still like reapply your own thinking to solve, like, okay, this character is related to this character in this way. So basically, you can think of it as a graph also, like, given certain entities and certain edges. So the edges are essentially denoting relations. And if you want to do relation prediction, that is, what is the type of a particular edge, then in this kind of a kinship relation game, you can easily do that by taking like a walk over the path and basically resolving that path. So one of my previous work is named Clutter, which is exactly this. So Clutter is essentially a diagnostic benchmark, which is created for evaluating inductive reasoning from text. It is exactly a kinship relation game, where the model is essentially given a blurb of text, which contains a story. And it's a Q&A setup where you're given a question, and then your model has to give out an answer on all possible family relations. Now, each puzzle is built using first order logic. Now, that helps us a lot in basically making sure that all the puzzles are verifiable and the logic is built on a set of rules. Now the generator is basically fed a set of rules that we know about family relations. And then the generator essentially reapplies these rules to create this intricate puzzle. So this puzzle has essentially two modalities. So it has the primary modality is the text, which we want the models to perform. And then there is a secondary modality is graph. That is, each puzzle also has an underlying graph. Now, this is also a kind of a diagnostic suite. You can build your own complex setups on top of this, and then you can see how your models are systematically generalizing. Now, just as an example, so this is an input document. This gets fed to the model, and then we have a query. So in this case, we have a query which is a pair of entities that we want the relation in. Interestingly, we didn't use a natural language question that you see in a lot of Q&A datasets, because there was a really nice paper in AMNLP 2018, which shows that a lot of these models, they do not even understand the entire context of the question. So let's say if there is a question is that, when did this event occur? The model kind of performs even well if you like cut off all the different words and still focus on the word when. This is like a really great paper by Zachary Lipton. I would suggest you all to read it. And so basically, like we replace the question with the set of like queries. And then the task is simply to predict what is the relationship between them. Now, this seems very simple. And I have like heard from a lot of people that they are saying that, okay, this is very simple because you just have a set of rules that the model have to learn. And once the model learns the rule, and then it should perform well, right? So it turns out no. Why? Let us go towards a bit of the tasks first. So one of the tasks or the primary task that we want to look at is called logical generalization. So in logical generalization, you're given a set of like puzzles, which are kind of restricted by their length. So essentially, you're given a lot of examples, but you're restricting the length of this puzzle to only contain relationship combinations of length 3, and then you're testing on puzzles which has relationship combinations of length more than 3. So this is equivalent to the example I gave before, that if you know how relationships work, if I give you a long passage, you can still solve that given enough time and compute. So this is exactly the notion of system 2 deep learning, because the models have to think. The model have to like reapply their own skills over and over in order to solve this particular task. And also, we looked at a case of linguistic generalization. So essentially, we thought that, okay, a lot of NLP models are pretty good these days because they kind of learn a lot of features about the individual words. And then they, whenever they find the similar words, they kind of overfit on top of that. In order to like in order to make sure that the models are not doing it, for each puzzle, we have two representations of each puzzle. One representation is drawn, like basically each puzzle is a graph, and then you're applying a layer of language on top of it. And this layer of language is what we are collecting through Amazon Mechanical Turk. And essentially, we are splitting the placeholders of the Amazon Mechanical Turk into training and testing. So this becomes really challenging for the model because the model has never seen the exact syntax before. But if the model understands how relationships work, then it should be able to generalize better in this kind of setup. So, and also a third cool thing that we had in Clutter was robustness test. So as I said that since these are built on logic, you can easily verify whether your logic is sound or not. So let's say, given in this example, if I have given you a family relation tree like this, and let's say I want you to answer what is the relationship between A and D. So then there can be two possible paths in the supporting fact. And then your model has to understand, okay, since there are a supporting fact, I have additional information to do well. While if I have a tree which has a dangling path, that is kind of a confounder. And that confounder is like used to make sure that, okay, your model does not perform well, but your model has to understand, okay, I do not want to go through this path. And then there is a disconnected fact where you have a edge which is entirely disconnected from your like your current resolution path, but then your model has to also disregard that. So these are really simple but very powerful robustness tests that we have in Clutter. And so let's go towards like what are the models we initially used. So we essentially thought, okay, we have made the task really difficult for the text or the natural language understanding models. We also need to provide a benchmark for a model which do not have to do the parsing. So we used a graph attention network, which worked solely on top of the raw graphs. And for models that have access to the text, we used a vast number of models, including transformer style models such as BERT and BERT LSTM, which is essentially a layer of LSTM on top of BERT, on top of frozen BERT, essentially. So how does the models fare on generalizability? In the plot on your right, you see that the generalizability or the accuracy during testing drastically falls down when we show tasks of more and more length. While if we provide more training data, like if we provide the model training data of involving 4 number of relations, then the model like performs somewhat better. but the graph neural network performs the best when given a lot of additional data. But still, the generalization towards like extreme generalization, what I say, like towards the end of the number of 10 relations, then all the models kind of falter. But graph neural networks are really robust. When we use the different robustness test, we found that the graph neural networks almost always outperform all the text question answering models, which is understandably so because the graph neural network do not have to do the semantic parsing. So semantic parsing is one problem, but still the graph neural networks falter on the length generalization problem. So basically, clutter was based only on 15 rules. And these 15 rules were kind of a very boiled down set of family relation rules, which we used in order to make sure that the puzzles do not have any ambiguous relations. Now, how do we evaluate the adaptation of the models to different rules? Now, why is adaptation important? It is important, let's say, for example, in recommender systems, you have your model which is trained on production for certain products, and now your company wants to sell some other product. Now, you have to adapt on this new data of products because you have to learn the relationship between these new products. But if your model already knows how to pick up these relationships, it will be able to pick it up really well on this new data. And also that would be really useful later on for smart dialogue agents, which will be able to like converse with you based on some prior information that you have already shared with it. Also, we want to know in system 2 deep learning that how do we remember old rules? For example, when we are going forward to newer and newer tasks or newer and newer rules, do we still remember the old rules that we learned before? So these are the three key requirements for logical generalization. We want to inductively reason to unseen compositions, which is compositionality. We want to learn to adapt new rule set, which is multitask or even meta learning. So these are two different sets of problems. In this paper, we only looked at multitask, but meta learning can easily be done on top of this data. And we want to see how does the models remember the learned rules. So given a new set of rules, the learner should not forget what it has learned before. So now we come to the current paper, which is again another data set, but this data set is focused purely on graph because in the previous paper, we found that the graphs have performed so well. So then we thought, okay, let's see how far we can stress test graph neural networks. And this is a multi-purpose, multi-relational graph dataset, which is built using the rules of first order logic. But unlike clutter, so clutter was only built on top of 15 rules, and still it was challenging enough. In this work, we went a bit more crazy. We generated a large bunch of rules, and then we said, okay, once we have generated this large bunch of rules, we want to basically sample rules from this large set in order to create different worlds. Now, different worlds essentially mean different buckets. So each bucket contains a set of rules, but these set of rules are overlapping with each other. So let's say there could be a scenario where there are two worlds. The two worlds have the exact same set of rules except one. So then that two worlds are kind of 95% similar based on the number of rules that are available. So that gives us a really nice way to define similarity. And similarity is important because it helps us to define how far your task is going out of the current distribution. So when people are interested in out of domain distribution, the standard problem that people face is that there is no such metric on different data sets to define what is exactly an out of domain distribution. But if you define your data set based on standard first order logic, you get a really nice interface to do that. And that's exactly what we did in GraphLog. So essentially each world, so these are like W1, W2, Wn, these are different worlds. And each world consists of 5,000 graphs in training, 1,000 in testing. And then these different graphs, so essentially we had a total of 57 different worlds. And the number of graphs are also quite large because there's 5,000 in each of these worlds. And also each world has its own world-specific graph. So basically, what is a world-specific graph? So essentially, when we are generating graphs for each world, we first generate a huge graph. So this graph is basically generated by applying all the rules over and over and over and over. And when you have this huge graph, you are sampling smaller and smaller graphs from this huge set. And so these smaller graphs essentially become your training set. But then another sample of this huge graph is your context representation. Now, why is context representation useful? Because if you want to do multitask learning, if you do not have any sense of context, then the models would essentially not perform well at all. Because the model is essentially learning some objective function in some task, and then it is switching to another task, and then it would drastically not perform at all. So what would be a context here? So since we are looking at a relation prediction, the context are essentially the relation embeddings. And since we are providing a world graph, a model can take that world graph and then output certain relation embeddings that would be useful for that particular world. And then the other models can take that particular embedding and then work on top of it for that current world. So it's very easy to compute similarity. It's very easy to compute out of domain distribution. And so with this help of 5,000 graphs in each world, number one, you can perform supervised learning as usual. So the supervised learning essentially consists of the compositionality test, because in the test set, you are essentially figuring out the unique compositions of relations which you have never seen before. Like you are given to predict the edge or the relationship between a source and a sink, whereas the composition or the walk between the source and a sink is unique. And then you can do multitask learning. On top of all of these worlds, you can train your models to do multitask learning. Essentially, that means that you're training on one world at one epoch and another world, another epoch. So essentially, you're trying to learn all the world information at the same time. Now, in the beginning, we said that we had this set of rules generated in the beginning, and then we are essentially doing a subset on this set of rules. So that means by doing a multitask learning, you will never go into the region of invalid rules, because all the rules are generated at the same time. So all the rules are already made sure that all the rules are consistent with each other. So by doing this kind of multitask learning, you won't have to worry about whether the rules that you're learning in world A are inconsistent with the rules that you're learning in world B. Sure, these two rules can be very different, but if you're putting it together in the same model, there wouldn't be an inconsistency issue. And finally, you can do continual learning. So this is highly exciting, because our work is one of the first work in graph datasets which has this like added objective of continual learning. And there's a lot of recent work, exciting work coming up in continual learning, where people are trying to figure out how to basically see that whether your models are learning to remember on previous tasks or not. Given this set of world splits, we can define each task as individual world split. And that is our like proposal of doing continual learning purely on top of graphs. So before I jump into the results, so I want to like talk a little bit about the models that we use. So essentially, we used a lot of models involving RGCN, which is a popular model used for relation prediction, and graph attention networks, and GCNs also. Now, as I said, when you're trying to do multitask representation, you want to have a context. And how do you get this context? So basically, we divided the model into two parts. One is a representation function, which takes into input the world model, the world graph. So essentially, each world has a unique world graph. And this model ingests the world graph and outputs the set of relation embeddings, which are contextual for that current world graph. And then another function, which is the composition function, which is also another graph neural network, that takes these relation embeddings, and it takes all the different 5,000 graphs and tries to predict the missing relations on top of it. So in this kind of domain, we took a lot of combinations of available like composition and representation functions. So a very simple representation function can be just a parameter, or like just a weight lookup, or basically like an embedding lookup in terms of an NLP. So why that wouldn't work? Because an embedding lookup is essentially learning to like backpropagate to each relations from all different worlds. So it basically does not learn any world specific information. So on top of that, we can optimize that by using a GCN and a graph attention network as our representation functions, which take into account the world graph and then gives you a set of weights, or basically a set of uh, relations to work on top of. So, and then the composition function is essentially a model which can predict relations. So this model has to operate on the edges, and RGCN was one of the really famous models which works on top of these relation prediction tasks. We had to modify GAT. So for the clutter task also, we modified GAT to attend over edge representations. So originally GAT, or graph attention networks, is basically during the message passing update, the graph attention network attends to the different messages that are coming in. But in our modified edge GAT, the graph attention network is attending to both the messages that are coming in and also to the edge representation of the source and the sink. So this EdgeGAT is also the same model that we used in Clutter, and that's why we use it here also. So how do the models fare on generalizability? So when we do supervised learning, we find a nice like a separation of difficulty of different words. So this difficulty is essentially like a separation based on the number of unique composition or descriptors available in each word. So in some of the words, the number of compositions are not enough. So essentially, for each of the graphs that we generate, these graphs also has the set of noise that you have seen before. So in Clutter, the types of noise that we generate, we also use the same types of noise here. So that adds a lot of other difficulty. And these procedurally generated words, when we do a supervised learning, then we have a nice like proxy, which is the supervised learning scores. And these scores are basically very similar to each of the different models. And that gives you how much easy or difficult each words are. Now we do multitask learning. Now in multitask learning, we increase the number of words, and then we see that we hit a saturation point at 20 words. So that can be an outcome of the number of parameters that we had in our model. Like if we increase the number of parameters, we can increase this number of saturation. But if you see the accuracy, even at 20 words, the highest accuracy is 60%. Whereas in individual words, the accuracy goes towards 80 to 85%. And then we also did multitask learning on the easy and on similar and dissimilar splits. So essentially, S is the similar split, where we took the words which have a similar set of rules, like which are not differing too much from each other. And D is a set of words which have very dissimilar set of rules. And then in both of the cases, we find that graph attention network and EdgeGAT combination is performing the best out of all different baselines. So now we look into multitask adaptation. So in multitask adaptation, we train using the multitask objective, and then we adapt based on the weights learned from this multitask objective. And we want to see two things. First, we want to see the final performance after adaptation. And then we want to see the adaptation speed. And during this, so just a clarification, this is not traditional meta learning. This is just simple multitask learning, and then you're adapting on the weights that are learned on the multitask learning model, which is very similar to what we do in transformer models, where you do pre-training, and then you basically fine tune on your given task. So in the graph you see on the left, on the orange like bar is one that we represent, which has very dissimilar set of rules. And the blue bar is the one where we have a very similar set of rules. And what we see that for most of the models, when we do multitask training on dissimilar set of words, then the final adaptation is much better than when we train on similar set of words. So this is a very nice finding, and that kind of correlates with a lot of pre-training literature, that whenever you're doing pre-training, you should try to incorporate as much dissimilar set data points as possible in your pre-training pipeline. And similarly, we see that when we look at the gradient updates, the models which are trained on dissimilar set of words are faster in adaptation. And finally, we come into the results of continual learning. In continual learning, we have two plots. So the blue plot is essentially the current task performance, and the orange plot is the performance of the mean previous task performances. So the mean of the previous task performance is basically falls down rapidly, and also it's pretty bad. And that is where we need to like improve a lot in graph literature. And this data set essentially gives you a very, very challenging benchmark to do continual learning. So in the second plot, I'm showing the continual learning results when we ordered the words in terms of its difficulty. So recall that we got a difficulty score while doing the supervised learning training. So we ordered the models according to the difficulty score. And then we see that the single task performance is according to the model, but then the mean of previous task performance is also pretty bad. And that needs to be done. So basically, there is a lot of grounds to cover in terms of continual learning. And we believe this is a really, really challenging benchmark for it. So essentially, the key takeaways in GraphLog is that training on diverse datasets improve the generalization performance, and pre-training on diverse datasets also help to adapt to newer datasets. And pre-training on difficult datasets improve the model adaptation ability. So difficult also includes like dissimilar datasets. But if you read the paper, we also have a topic on how easy and difficult training works in these kinds of setups. And we essentially have a lot of work to do in order to perform true lifelong learning in graphs. So in the conclusion, I show you like basically a snapshot of the two data sets that I've been worked on the last couple of years. And essentially, one of them focuses on the modality of graphs, while the other focuses on the modality of text. And for both of them, I have like released blog post. And for GraphLog, we have released an API, which is a really easy to install pip installable file. We also are looking to release the similar kind of API for clutter as well. And using this API, you don't have to worry about data loading. So I provide data loaders for you and easy to use experiments, and also easy to use scripts written in PyTorch Lightning for you to like run your experiments just like that. And we have a generator module for both of these data sets. The generator module for clutter is already out there. We will be doing a lot of like improvements based on user feedback on top of it. And also the generator module for GraphLog is coming out very soon. So yeah, that's mostly it. Thanks to my awesome collaborators, Shagun Sodhani, Jin for clutter, Joel and Will, my supervisors. And also thank to my amazing colleagues at Mila and Fair Montreal for all of their support. And if you have any questions, you can ask me now, or you can like send me a mail. Yeah. And also you can like join our logical ML Slack, which I've opened to answer more questions. Thanks.
Nice. Thank you so much. So we have two questions already. So I'll go ahead and do that. And then the YouTube folks, you can start asking your questions on YouTube and we'll get those for you as well. All right, so Mohammed asks, what if the relation is not defined from the text? Would the model still be forced to predict the value of the edge?
So yeah, that's a very good question. We made sure that the relations are always defined in the text. So that kind of error do creep in if you're working a lot with Amazon Mechanical Turk. And it's a very messy situation out there because you have to do a lot of like cleaning on the data that you collect. So we made sure that the data that we collected or the templates that we collected has all the relation identifiers, and without them you cannot like essentially solve the puzzle. So we made sure that you have the relation IDs.
Nice. And then the second question is, rules are super interesting. Is it possible to inject custom rules into experiments to see how
Sure.
they perform? Is
Of
it
course.
also possible? Oh, go ahead. Yeah,
Yeah.
just answer that one
Yeah,
first.
so that's a really nice question. And yes, it is possible. For both of the data sets, for clutter, you can just easily like edit a YAML file and do the generations. So in the YAML file, the way I define the rules is it's essentially a first order horn clause. So the horn clause is essentially a rule which has like a body and a head, where the body composed of like two entities and a head is the output of that entity. So you can inject rules in that fashion. In case of GraphLog, we are essentially generating rules on the fly. So we are not using a single YAML file. So in case of GraphLog, what you can do, you can tweak with that rule generation parameters. So there's a lot of parameters which says that, okay, how many symmetric rules we will have, how many like invertible rules we will have, and so on. You can increase the set of rules like to a lot. Like if you want to do massive experiments, you can just play with them. Like both are essentially data set generators.
And then a related question, is it possible to extract rules created and understood by the model?
Yes. So your question is whether it's possible to extract the rules that are understood by the model. So this is a very interesting research direction on its own. For graph neural networks, there is like several papers which look exactly at this problem. Like using graph attention networks, they try to like predict which of the edges that the attention are like kind of highest, and those are the edges that the model is kind of perceiving. We haven't done that kind of experiments in here, but that would be a really interesting way to look at it.
Thanks. So those are all the questions, but
I had a follow-up or related question actually to Mani's. So you presented for the clutter work, you presented some stuff about generalization to relations, like longer sequences of relations, reasoning to longer sequences. So back in the early 90s, some folks did work with RNNs to do addition, and you used addition as an example of a similar problem. And they looked at how long, like how far out could they, like how long digits could they add together. And they were able to extract from the RNN an actual dynamical system that the RNN was implementing approximately that could do addition to basically infinite precision. Basically, you know, like it was they could find a set of weights that could then do even better than the network had done on the task. So that used some of this sort of specific ideas of RNNs, but I'm curious if for some of these like logical ML things that get closer to you know, traditional computation, if there's any hope that the networks that we're building and learning, that we might be able to extract back out from them an algorithm, something interpretable, something that's like compilable down to traditional code, or whether you think that that's a gap that can't be crossed.
No, that is also like an exciting research direction, what people do in program synthesis. So essentially you are trying to like generate the programs which you are essentially you're trying to optimize the programs that you generate and on your particular task. So there is a lot of research going on there. And I'm not super familiar with the research literature, but the way you mentioned it, it would be like possible. Like you essentially generate a program that will do kind of a recursive computation on top of this data set, and that recursive computation model is basically what we need. But that is also like super hard, and I would also like term that as system 2 deep learning, and that is what we want to move towards.
Nice. We have one more question from Heinz. For those who are not familiar with graph neural networks, do you have a sequence of papers that you recommend that people read, or other resources?
Sure. For graph neural networks, I would suggest to start from the basic GCN architecture by Thomas Kiff. And then you can look at Peter Velikovic's graph attention network, which is really popular. If you want a condensed survey, so my supervisor, Will Hamilton, will be releasing a book very, very soon. So we are super excited. Like we actually like use that book for our course this semester. So that book will contain like a really, really nice in-depth overview of the entire theory and the applications. So just look out in his website. That's all I can say.
Is there publishing deadline for that yet? Or like when is it coming out? Do we know?
That I don't know. I have to ask him.
Cool.
But it
Cool,
should be coming out soon.
Nice.
You can actually find the online draft on Will's webpage. So Will's webpage, Will has a link towards his course, which is Comp 767, and in that, or it was 766, yeah. So basically, in that course, you will find the list of notes, and those notes are ones that he will compile towards his book.
Nice. All right, those are all the questions I see. Thanks, Charles, for sharing the link. Koustuv will be in our Slack community at 9 a.m. on Friday, answering more questions. We'll dive deeper into his paper. It's going to be a great time. Yeah, thank you for coming.
Thank you so much. Thank you.